We now turn to the question of how to solve equations where we've got mixtures of function families. What I mean by that is you might have some polynomial elements alongside maybe exponential or logarithm functions. So a mixture of different kinds of functions in the same equation. In general, we have to have some pretty special cases in order to be able to solve these equations by hand. So I'm going to show you a few examples of that, and then we'll look at what else we could do if we're not in one of those special cases. So here's the technique I'd like you to try in these next couple of examples. First, we're going to want to get our equation equal to 0. Not uncommon, right? We're kind of used to that. And then try factoring out a GCF. See if that gets us anywhere. All right, here we go. My first equation, x e to the x, equals 5x. Notice I've got an exponential function, e to the x, and then just over here is just a linear function, right? So it's a mixture of a polynomial with an exponential. I'm supposed to get it equal to 0, so I am going to subtract the 5x. And then I want to try factoring out a GCF. The only thing I see in both terms is the x. So I'm going to factor out the x, which makes that e to the x minus 5. Now our usual technique for solving once we've factored, set each factor equal to 0. So x equals 0, or e to the x minus 5 equals 0. X equals 0 already gives me a solution, but this is going to give me a second solution. Isolating the exponential, I would have e to the x equals 5. And then to get rid of the exponential base e, I use a natural log, doing the same thing on both sides. Exponential, or inverse functions rather, gets rid of each other. And so I just get x equals the natural log of 5. If I want to stick with exact answers, or of course I could just do a natural log of 5. And it's about 1.609. Okay, but two solutions. Let's try another one. In example B, it's already equal to 0, so I don't have to worry about that part. I'm just going to start out by factoring. Now certainly there's x to the first that could be factored out. But since e to the x is in both terms, I can factor out an e to the x as well. In my first term, the only thing that's left is x to the first power. And in the second term, the only thing that's left is that plus 2. All right, set each factor separately equal to 0. So x equals 0. E to the x equals 0. X plus 2 equals 0. X equals 0, already one of my solutions. And this guy comes pretty quickly as well. X equals negative 2, another solution. But what about this one? E to the x equals 0. Well, we've been saying that to get rid of an exponential base e, we would use the inverse function, the natural log, on both sides. X or inverse functions do get rid of each other, so that's just x. But think for a moment about the natural log of 0. Remember what kinds of arguments we can have in the log function? Just positive ones. 0 is not positive. In fact, the natural log of 0 does not exist. If you try it, calculator is going to give you an error message. So, does not exist. So in this case, the two solutions that we found up here are the only two solutions. All right, like I said, kind of have to have a pretty special case where factoring works out in order for that to happen. More often, when you've got a mixture of different function families in your equation, we just can't solve it by hand. Fortunately, using technology, we know a method already that will allow us to solve any equation. Right? What we've been doing is first of all getting the equation to equal 0. So the equation takes on the form f of x equals 0. Right? If we now graph the function y equals f of x, since I want to know where it equals 0, we will use the graph to find the zeros by looking at the x-intercepts. And that's how we'll get our solutions to our equation. Just a reminder, this only finds real valued solutions. It will not find any imaginary solutions. But in this section, we've been really concentrating on the real valued ones anyway. So let's see. Oh gosh, I forgot to start my Desmos. Let me see if I can get it into my space. I think I will be able to. All right, so we're going to solve this equation. 1/5 x equals the log of x plus 4. Notice that even if I got this equal to 0, there's really nothing that I could factor out here. So I'm kind of stuck with this one. Let's see if I can get Desmos in the right window here. I think we can work with that. All right. So first of all, I need to get my function equal to 0. So I'm going to rewrite that as 1/5 x minus the log of x plus 4 equals 0. And then I'm going to graph this function. And looking at my graph over here, looks like I've got 2 zeros. One there and one there. So I'm just going to give us a quick little sketch here. This first 0 was at x equals negative 3.828. And the second 0 was at x equals 4.697. Remember, you're only solving your equation for x, so it's the x values we want as our solutions, not the points, just the x values. All right, let's try another one. Get this lined up right. There we go. B asks us to solve 3 to the x power equals minus x plus 5. Again, I can tell you just from here that nothing's going to factor out. So let's get it equal to 0. 3 to the x plus x minus 5 equals 0. And I'm going to graph that function right there. There we go. And this time it looks like I only get one x-intercept. Kind of looks like this. And that x-intercept corresponds to x is 1.212. Remember that if you're ever concerned that you might have missed something because maybe the graph comes back up or something, you can always keep on zooming out long enough to say, you know what, it sure doesn't look like this is ever going to come back up again. I think I had the only 0. All right. In C, I have a factored form right here, and it's fine to leave it like that, although I personally think it's a little bit cleaner if I just multiply it out by distributing the x. But once again, looking this through, nothing's going to factor out. So I'd like to get this to equal 0. Subtract x squared, subtract 6x. And since there's nothing that's going to factor, I'm going to go ahead and graph that and see if I can find the zeros. There we go. And I definitely identified 2 right away. I won't sketch the graph this time, I'll just write them down. X is about 0.804. And actually, I haven't been using the wavy equal signs, but I probably should, because these are definitely decimal approximations. And the other x is about 2.044. I think that's probably it, but again, if I zoom out, oh, you know what? I get surprised. There's another one. So it just illustrates the importance of getting a big picture, right? Make sure you've seen everything interesting on your graph before you quit. So we're going to add another x value here, negative 6.163. And I'll do it one more time just to make sure, but that's starting to look, yeah, I don't think that's coming back down. All right, I think we got them all. One more equation over here. Natural log of x equals 2x minus 1. Natural log of x minus 2x plus 1 would equal 0. So there's the function that I need to graph. There we go. And I'm zoomed way out. Let me go back to a home screen for a second. This one doesn't seem as though it's going to cross the x-axis at all. So right now I'm guessing no solutions. But again, let me graph or zoom out a bit. Yeah, it doesn't look like it's ever coming back up. I think this stays below the x-axis all the time, never crosses. So there are no solutions to this equation. All right. We're going to finish up this section with sort of a little thought experiment. Sometimes they're called Gedanken experiments, German for thought. Probably because you're never going to get anybody to thought experiment, because you'll never get anybody to actually do this. It would involve them paying you tons of money. Here are the 2 options in our think experiment that we're going to have. Option 1, you're paid $1 million on the first day, $2 million on the second day, $3 million on the third day, and so on. Or in other words, your payment increases by $1 million per day. Option 2, you're going to be paid a penny on the first day, 2 cents on the second day, 4 cents on the third day, and so on. In other words, your payment is doubling each day. Which is the better option, and on what does your answer depend? Well, let's see if we can at least start by thinking about what the better option would be by modeling these 2 possibilities. So let's see. If I make a little chart for option 1, T would be days, and A is going to be the amount in dollars that we are being paid. So on day 1, we're paid $1 million. Day 2, we're paid $2 million, and so on. All right, in option 2, I'm going to set up a similar chart. And this time on day 1, we're paid 1 cent. On day 2, that doubles, we're paid 2 cents. On day 3, it doubles again, so 4 cents. On day 4, it would be 8 cents. On day 5, we're all the way up to 16 cents, right? Of course, over here, the 5th day, we're making $5 million. So right now, this option is looking pretty good, right, as compared to that one. Let's go ahead and see if we can come up with a mathematical model for each option and see what they look like in the long run. Thinking through this very first chart, it looks like we are adding $1 million every time, right? And in fact, that's exactly what we're doing. We're increasing by $1 million each day. So adding the same thing each time means we're in a linear situation. Y equals mx plus b. Okay. In this case, we already know the slope. The rate of change is $1 million. And the b value here, well, let's see, I don't have 0 in my chart, but if I kind of project backwards, I'd have to subtract $1 million. So basically 0 would just be 0. And the equation that models this option is, oops, sorry, I don't know why I used x, I'll use t, 1 million t. All right, let's look at option 2. Here, if I look at the pattern, I'm doubling each day, so I'm multiplying by 2. When we had something going up by a common addend, we used a linear function. But when we're going up by a constant multiplier, this time we would need to use an exponential function. Y equals ab to the x. Come back to a in just a minute, but notice that since the constant multiplier is 2, that means our b value is 2. And again, I'm going to go out to t because I had t in my chart. Okay. I do need to find the a value, and again, I can either predict or I can plug in a point and solve for it. It's not that hard to predict really though. If I go back to 0, see I'm multiplying by 2 coming this way. I would have to divide by 2 to go back up. So 0.01 divided by 2 is 0.005. So that's my a value. And there's my exponential function. All right. In order to explore what happens to this as time goes on, we're going to go ahead and graph both of those. So first of all, the one that starts us out with $1 million a day and adds $1 million every day. Was 1 million t. Really large numbers here. Let's see if I can get this to the point where we can actually see the line look like something besides a vertical. There we go. So there's our line representing 1 million times how many days it's been. That's our daily payment. All right, let's graph the second one. Let's see, I can't call it A, so I guess I'll call it B of t. That was 0.005 times 2 to the t power. And not surprisingly, looking out here, it does not look like a very good option at all. These payments are way lower than these multi-million-dollar payments up here. But look at what happens if I start to go out a little further. Right here, on day 32, 32.6, but somewhere between day 32 and 33, the amount of the payments that started out with a penny, the exponential function, actually become equal to the payments from the $1,000,000 a day increase situation. So right there we're getting the same amount of money on about the 32nd or 33rd day. But then look what happens after that. There's that 32nd day again. The $1,000,000 a day still goes up pretty well, but look at how fast the doubling version goes up. Much, much more quickly. So in the long run, the one that started with the penny and doubles each day is actually going to pay off after about the 32nd day. You're going to be making more money per day than you were with the millions. Let's write down that much first. So the linear function is much larger at first. But this one, the exponential function, catches up on day 32. And surpasses by a lot on all the remaining days. So the quick answer is, it's actually better off to pick the one that starts with a penny, right? However, keep in mind in real life, this would depend on how quickly you needed your money. If you were doing this and you needed the money in 2 weeks, you'd still be better off with the linear function, the one that goes up by $1,000,000 at a time. As long as you can afford to wait past day 32, however, you're going to be better with the exponential function. All right, last thing. Many people say that something grows exponentially anytime they see something increasing quickly. And when you think about our picture, you can kind of sympathize with that, right? See how fast that exponential function goes up. However, do you think that that is an accurate use of the phrase growing exponentially? Just growing fast isn't enough, right? This line grew very quickly. It grows by $1,000,000 a day. That's a lot, right? So it's going up fast, but it's not an exponential growth. It's still a linear growth. Most people in everyday life don't really use the word grows exponentially in a correct manner. They just mean it grows fast. What we mean mathematically is that it grows by a constant multiplier. And that's what makes it exponential. All right, that brings us to the end of section 5.6.